My plan is to have the midterm available on Sakai on Thursday, the 24th. Another way of putting it is that your final questions to me on preparation for the midterm will be in class on Thursday, the 24th, and then right after that, the exam will go up. Today we will finish the lectures in the area that's called scale and locality and move on to a short section on interpolation in images. And the PowerPoint set for that is up on Sakai if you want to bring it up on your computers or something now to follow the lecture or take notes on it. You can take it from there. We will take a break from the ordinary lecture subjects next time to go back and do the review of the first half of the course, the material that the exam is on. It would be good if you brought questions during that lecture, and as they come up in the review of the material, you interrupt and ask relevant questions. I realize I hadn't made a distinction for you clearly enough. And there's a problem with the frequent usage, I dare to call it misusage or misleading usage of the word resolution. And I wanted to clarify that. The word resolution has to do with how to resolve something, that is to say, how to tell the difference between two things. In particular, the original notion, long before there were ever digital computers, came from separating two bars. And that's the basic meaning. Can we resolve two bars or do they appear as one bar? Okay? The question that you had on the homework due today was about resolving two bars when the bars are imaged with a particular camera that has an RMS width of sigma. Okay? But the point is that it's about resolving two bars. And there are two forms that basically need an adjective to describe them. One we call optical resolution, and that's resolution due to the blurring. And blurring, you have an RMS width of the blurring that, for example, came from a camera. When I say camera, I'm talking about a generalized thing. It can be an ordinary light camera. It can be a CT imager, an MR imager, an ultrasound imager, a seismograph that takes images of things under the ground, and so on, right? But the point is that these devices that result in an image can have do have a point spread function. And if you figure the RMS width of that point spread function, the basic idea is they're all roughly Gaussian shaped. The point spread function, the RMS width of a Gaussian is its sigma. And so we'll call RMS width sigma altogether. And then the ability to separate bars is proportional to sigma. Okay, so we can say sigma or some multiple of sigma is the resolution of this imaging device. The resolution provided in images provided by this. Well, when computers came along, digital computers, we represented images in terms of pixels or in 3D voxels, right? And they had separations delta x. And if you put two bars in adjacent pixels, you couldn't see two bars. You just saw a slightly fat bar. But if you put them 2 pixels apart, then you could tell one bar from the other, right? If you had a background intensity and 1 bar and 2 pixels over another bar. And so we can and should call that pixel resolution, right? And unfortunately, computer scientists, because they're stuck in the world of computers, use the word resolution frequently to mean pixel resolution, forgetting that there is also optical resolution, and that's relevant to them as well. And so I ask you, as you go forward in your career, to put that adjective on and make it clear whether you're talking about pixel resolution, where things are proportional to delta x, or you're talking about optical resolution, where things are proportional to RMS width sigma. And of course, what we learned was, if we optimally sample, delta x should be proportional to sigma. So everything would be, if we properly sample, everything would be proportional to each other, if you will. They'd all be resolution. Is that clear? Is there any question about that language use? Okay. There's a little section here of stuff that we've already gone through in this course on edginess and barness. You've had homework assignments on each. I've talked about them in lectures multiple times. I'm not going to repeat myself at length. But the basic point is that there are operators on images that measure edginess and barness. And in this section, where we're talking about scale, the critical question we want to talk about is, yeah, but what scale do you measure edginess and barness at? Okay, and we've already talked about that. That is to say, first of all, we've talked about directional derivatives. And directional derivatives are taken at scale. We've said there is a Gaussian. You need to think that there is a Gaussian applied to the image when you want to take a derivative. And because of the way the operators commute, you can take the appropriate derivative of the Gaussian and then apply that to the image if you want to think of it that way, right? So these derivatives that we use to measure edginess and barness are going to have a scale. And the question obviously is, well, what scale? Right? What sigma should we use to measure them? And in the case of the edges and barness operators, there's not only scale to choose, but a direction to choose. And we've talked about how to figure out what directions to take first or second derivatives of. First derivatives depending on the optical resolution of our image, or in other words, the RMS width associated with the formation of our image. And we said that we would like the slope at an edge to be matched to the derivative operator, its slope at the middle of the edge. Okay? And we said that we would like for a bar, we would like the bar width to be matched against the sigma of the second derivative operator that we use. And so we end up with barness taking an optimal barness, which happens to be an eigenvector of the direction is an eigenvector of the 2 tensor. And sorry. And this has to do with the notion that to measure, to get a response to a particular property, we want a filter that is as close as possible matched to the object the entity we're trying to detect. And so the first derivative operator has an edge, and an edge at some slope. And that slope depends on sigma, and we should choose the sigma, so its slope matches the slope of edges that we have in the image. And the same thing, matching the width of the bar with the width of the central lobe of the second derivative operator. Okay, so I'm just trying to bring together the notion of matched filter and these ideas of the derivatives and how the scale is related to this matching. Okay, any questions about that summary? I'm now going to go on to the issue of noise. And in the case of noise, we understand that we think of images as being made up of, I'll call it I signal, plus some noise, and we understand that the noise directly out of an imager is typically white. That is to say, it's uncorrelated among pixels. The variation from the signal in one pixel is essentially independent of the noise in another pixel. To take some examples, in radiography, X-rays, you have essentially photon counts at every pixel. And they're especially apparent in nuclear medicine images, in so-called scintigrams and PET images, and so on. The fact that you have individual photons essentially being detected means that if you had a source that should have provided, let's say, 1,000.235 photons, okay, on one random imaging thing, that pixel would have 1,000. Some other times it'd be 1,001, some other times it'd be 998. They're going to be integer number of photons, right? I can count them. And they're not always, each time we run the experiment, we're going to get in that pixel a different number of photons. And the variation of the 998 that we get this time from the 1,000.23 that the signal should have been, because that has to do with whatever's in the scene, that value of whatever I just said, minus 2.23, is the noise. It's this n of x, right? And we're going to be talking about how we understand this term with respect to scale. Okay? Now, before we do that, we need a basic piece of, call it mathematics or applied mathematics or physics or whatever you want to call it. And it has to do with analysis of variables in terms of their units. Okay? So, if you want to read about this, you'll find it discussed in the Teharomany book that I have given you reference to and is on reserve. none of you have yet asked for the CD, but again, I repeat, if you want it, you can have it. Anyway, the point is that if you have something where you're adding two numbers, they'd better have the same units. It makes no sense to add centimeters to seconds. You can add something in units of seconds to something that's in units of seconds, or something that's in centimeters to something that's in units of centimeters, but adding and subtracting without having the same units makes no sense. And with multiplication and division, here's a multiplicative situation. The units of the product has units which are the units of one of the multipliers times the units of the other multiplier. Right? And so you can forget what the actual numbers are and just think in terms of the units. And so if, for example, you have something that is a scale value times the derivative of an image, the units of scale are spatial units. For example, centimeters, right? Okay, so we'll use centimeters as our basic units. We can turn any spatial units into another by a multiplier. But anyway, so these are spatial units, it's in centimeters. di by dx, you want to think of as basically a limit as delta x gets small of delta I, in other words, I at some place minus I at some other place, which is the difference of two things that are in intensity units. Okay, if we have a camera, the intensity units may be lumens. If we have a CT image, it may be Hounsfield units, right? Those are the units that describe intensity in a CT image, right? And so delta I is in Hounsfield units. So I is in Hounsfield units. So delta I is also in Hounsfield units. Delta x is in centimeters. And so a derivative, its units are the intensity units, in this example, Hounsfield units, divided by centimeters, right? Derivatives of images are in intensity units per centimeter. And now sigma is in centimeters, and so if you have centimeters times Hounsfield units per centimeters, the centimeters cancel, and you get Hounsfield units, right? So you just play this game of units where you treat them as things you can cancel or multiply by. Another example is the second derivative of an image. Well, second derivative is the first derivative of the first derivative. Right? The d by dx has units of 1 over centimeters. It's got a 1 over delta x. We've already talked about that this di by dx is in intensity units divided by centimeters. And so a second derivative has units of intensity units per centimeter squared. Right? The main thing you need to learn here is that this unit analysis is useful, and it's important because when we're going to think about, for example, the effect of noise at some scale, we're going to have to be mindful of what the units are in question. Okay, so what I've just argued the first derivatives are in units of intensity units per centimeter, and second derivatives are in units of intensity units per centimeter squared, that is to say, different units. If you ask me how much time is worth how much distance, well, Einstein thought about that, but when he talked about relativity, but nevertheless, the major point is that in ordinary understanding, you can't talk about how many seconds are worth how many centimeters. It doesn't make sense to compare seconds to centimeters. Likewise, it doesn't make sense to compare derivatives or Noisen derivatives over the order of the derivative. That is to say, to compare errors in first derivatives to errors in second derivatives, because they're not in the same units. They're so-called not commensurable. Okay? So we need to make them commensurable before we can talk about them. And a reasonable way to do that is to consider for any kth derivative, we need if we consider sigma to the k, which is in units of centimeters to the k, times dk, which is in units of intensity units divided by centimeters per k. Now we can compare derivatives. We can compare sigma to the 0, the noise in sigma to the 0, that is to say 1, times intensity with first derivatives if we think about sigma times the first derivative and not just the first derivative, right? Or if we want to compare second derivative, we need to compare sigma squared times the second derivative, right? Because again, that's in just intensity units. And so, well, why multiply by sigma? Well, essentially because the scale is setting, the spatial scale is essentially setting the units that you're concerned with, right? So we can indeed consider the sigma to the k. You could also have some constant times sigma to the k, but the literature has suggested that c equals 1 works about as well as you can expect. Okay, so the upshot is when we are taking derivatives of this image, let's say in one dimension, just to make life simple, if we have dk of I by dx, that's going to be dk of I signal by dx, which is sort of which is the signal for the k, x to the k, plus dk of the noise by dx to the k. And now, if we want to compare these noise levels, we really have to compare them multiplied by sigma to the k. So we're going to be concerned with not this, but rather with sigma k dk of n by dx to the k, when we're comparing different k's, the noise in different k's. Okay? And be careful, these derivatives are taken at some scale. There's always an aperture. right? And that's the sigma that we're talking about. So there is this position about that you will see in many, many places that you now will have to learn to say, oh, that's stupid. And it says, for example, that noise is badly propagated by taking derivatives. It's badly propagated at some scales and not badly propagated at other scales. And you can't make the statement doesn't make any sense because the units are wrong. To compare the noise and the original derivatives, you have to do the sigma multiplication to do the comparison. And when we do that, we get a surprisingly different answer. And again, you'll find this discussed in the Romany book. And this is the result that you get. The first thing to say is that when you convolve an image with an operator, for example, the derivative of Gaussian operator here, which is not really just a derivative, but a derivative taken with an aperture sigma, when you convolve the image with that Gaussian, you change the noise level. And how does it change? Well, we've talked about the fact that the noise level in an image is starts out as being white typically before we do any operations on it. And so there is this variance of the noise at any given position. That is to say, the mean square noise level, which is presumably the same everywhere in the image. Okay? Or it can be different at different places in the image. But anyway, we have this idea of the amount of noise, right? We have lots of noise, lots of variation in the level that we get when we have a particular signal level. What happens when we take that same image and we apply a kernel, little h? Here, the Gaussian kernel. But whichever kernel, and the answer is that the level of the noise, the variance in the noise, lowers by that factor, the integral of h squared to the half. So we know for any given aperture, where h is the Gaussian with that aperture, what the level is going to be. And so using a particular scale, aperture size, it turns out that in m dimensions, the output noise level is divided by sigma to the m over 2. And so in particular for 2D images, it's multiplied by sigma. It's divided by sigma, I'm sorry. And so the bigger the sigma, the lower the noise level. And for 3D images, it's divided by sigma to the 3/2. Okay. And when we take all that into account, and we look at the values of the noise as a property of image order relative to the level that was in the original image. Okay? So obviously you double the image, not the level of noise, the variance of the noise, or the standard deviation of the noise, the amount of noise. And the original image, if you double it, then you double all the way down, right? But relative to it, so we have the ratio here of the noise in some derivative multiplied by sigma to the k for the kth derivative. And this is a log scale because it's a ratio. And so this level at 0, log of something is 0 means the multiplier is 1, right? Log of 1 is 0. So 0 means it's the same. Well, okay, the level in the 0th derivative is the level at the 0th derivative. Sure enough. Well, I mean, that's just an object. And the interesting thing is if you plot this as with derivative order, you find that sigma times the first derivative actually has a negative logarithm. That is to say, it has a value that is a fraction, some fraction of the noise level in the original image, right? It's actually good to use first derivatives once you understand that there's scale involved. And the second derivatives is still a fraction, but not as small a fraction, but still better than the amount level in the sigma squared times the second derivative is still better than sigma to 0 times the 0th derivative. And only at the third derivative do you get actually an increase in the noise level once you understand it this way. And only by a little bit worse than the original. And the fourth derivative starts to get notably worse, but still not too bad. And you can see where this is going. And if you take more orders, it's going to get worse and worse. There's lots of evidence that the human visual system is, roughly speaking, taking derivatives. It's looking at edgeness and first derivative-ish things and second derivative-ish things. And there's some reasonable evidence that it's taking at least third and maybe fourth derivatives. And that's not surprising, given that evolution would have provided that, given this analysis that I've shared with you. Okay? Finally, realize that in the frequency domain, when we take the Fourier transform of all this, if this is new, and now this is what I'll call the Fourier transform of intensity, or in the case of noise, the Fourier transform of the noise. In the case of the noise at 0th derivative, we saw that it looks like this, but because we're applying a Gaussian, the noise level in the frequency domain actually drops and I didn't as a function of frequency. It's still a problem because the actual imaging drops faster, and so the signal to noise ratio, let me draw this at a different scale. If this was like this, then derivative is going to fall like this, but the image, which I'm going to draw in red, is going to drop faster. And so, starts way up high here. The point is that after a little while, even though the signal got higher than the noise level, the signal to noise gets worse past some level. Okay? What have I done with my pen there? It's another advantage of chalk. When you put it down, it doesn't go bad. Okay, so the final thing is that we've seen that for the frequency representation, 1 over frequency, which is wavelength, is a level of detail, right? And the main point is that all this analysis works for other orthogonal basis images. And I can talk about 1 over level of detail, whether, if I'm using Gabor variables, Gabor wavelets, or orthogonal wavelets, or any SVD-based basis images, or et cetera, et cetera, et cetera. The point is this general behavior is maintained no matter what your particular level of detail what particular level of detail you're talking about. Okay? So we've been talking about spatial scale. We have said we should make our measurements at whatever the appropriate scale is. We talked about scale space and the idea that we want to find things that are optimal in scale space, not just in position space, or in general in scale space times direction space, because we need to take our derivatives of bars orthogonal to the bars and our derivatives in edges orthogonal to the edges, and so on. And this idea of these optimalities in these complicated spaces that is an issue that we're going to call ridges. And we're going to talk about ridges in this course, but not till the end, to the last subject in the course. As I explained, I want to get to another subject that's so important that I want you to be able to do an exercise on it. And we'll not do an exercise on ridges. So I'll get to the ridges matter later. This is the last slide we've talked about these various decompositions of images in terms of bases. Some of them global bases, some of them bases with locality and scale. And the 3 basic ones we've talked about are the Fourier basis, the sinusoidal basis, the Gaussian derivatives, where order is level of detail. But now we can do that with locality. And the wavelets and splines, the wavelets, whether we're talking about the Gabor wavelets or the orthogonal wavelets, and splines. And we're going to see a connection between the wavelets and splines later. And those can also be done with locality and with various scales, and this whole multi-scale idea, just as the Gaussian derivatives. And then here's the story. The Fourier basis is completely lousy with regard to locality. It's applied globally in the image, and without an aperture where we move into the Gabor wavelets, it can't be applied position by position. Really awful with regard to locality. It has these nice invariance properties, right? It's not biased when you do things in orientation, for example. Okay? And because we have this super algorithm for computing those coefficients, namely the FFT, it's really, really fast. It buys you speed. That's what Fourier is good at. It's great at speed, it's crummy with locality, and it has good properties for invariances. The Gaussian derivatives, quite good with regard to locality, quite good with regard to invariances, not completely awful with regard to speed, but nevertheless, because you can do things in the frequency domain with them, but nevertheless not particularly speedy. The wavelets and splines are good with regard to locality, awful with regard to invariances. Right? You don't get translational invariance we talked about for the orthogonal wavelets. You don't get rotational invariance of the splines, so you don't get rotational invariances. And they're not as fast as Fourier, but especially with the wavelets where you have orthogonality, you can get half decent speed. Okay, to make a long story short, these are the basic methods that have been developed, and none of them is perfect, right? They all have their faults, they all have their strengths. And depending on what you care about, you pick one or the other, right? Any questions? This is the last slide in this scale and locality section of the course. We now move to a new section of the course. The topic is interpolation. And we're going to talk about interpolation via convolution. And we do convolution by orthogonal basis functions, especially the Fourier basis functions. We are going to talk about interpolation via splines. Splines are underlying, they're piecewise polynomials, right? And so we're going to be able to think about interpolation via splines as interpolation using piecewise polynomials. And when we recognize that images have noise in them, we don't want true interpolation at all. The word interpolation means, literally, that the values that you are interpolating between are their own results at those places. So let me erase some and so in one dimension, if we have points here, and we need a function that we're going to evaluate at any x that we want, if we're doing interpolation, we want some sort of a continuous function that passes through the actual points. So I didn't draw it perfectly. The point is, interpolation means that the value of the interpolating function has the value of the sample points at those sample positions. But if we realize that this sample point is really some other value which the sample point is just one sample. And so what we really mean is this with some tolerance. it makes no particular sense to insist that the interpolating function pass through the points. We just want the interpolating function to pass near the points. We've already seen, for example, in B-splines, that the ones we want to use aren't interpolating. They pass near the points, but not through the points, through the control points, right? And these are essentially, and so we will be interested in some kind of an approximation that passes appropriately near, but not through the points. And to do that, we're going to be talking about least squares approximation. Okay, so that's where we're going. We're talking about interpolation in this. So why interpolate? So we have some image, right? It's got pixels. In X and Y. Or in 3D in X, Y, and Z. And somebody says, yeah, but that image was taken when a person was being imaged straight on. And what we really want is to take, sorry, let's do it the other way. The person was slightly askew, and we really wanted the image when it was that way. And to make it into an image that we can put in some standard position, we have to rotate the image. And that's going to be a major topic of the next part of the course after interpolation, these geometric transformations. But the idea is when we rotate the image, the rotated image is going to have pixels that are and so on, right? And those pixels, those blue pixels aren't at the places where the black pixels are. When you rotate an image, you get new pixel centers. And therefore, when we rotate, we also have to interpolate. We have to figure out what the intensity is here, and we're going to do that by interpolation in the region of that blue place from the black pixels, from the original pixels that were in XY, and now we've got an X prime, Y prime, which is a rotated coordinate system, right? Okay, so likewise, if we do translation, we have the image, and the human body was a bit askew. You wanted it in the center of the image. And this particular picture had the body in the left side, and we want to get the body in the middle. So we need to shift everything. And now we're going to have new pixel positions from that. They're going to be shifted positions from the black pixels. We're going to, after rotation, let me find some red pen. Still have XY, but the positions are going to be translated positions. Okay? And so now we need to interpolate at the x's from where the black ones were. Right, from the values that we have in the image. The same thing goes for scaling. If we have to spread all the pixels apart, they're no longer going to, the new pixels at the new scale are not going to be at the same positions, that center positions as the old ones, and we're going to have to interpolate to get the new values. So this interpolation is really important. And finally, when we do deformation, all bets are off. Now when we do deformation, In some parts of the image, the pixels are going to, in effect, get closer together. The position of these black things after we deform is going to have modified black things that are scrunched in some parts of the image and spread in other parts of the image, not to mention also possibly rotated and scaled. And again, we have this whole problem of the new pixel centers after deformation correspond to non-centers of the original pixels. We understand deformation to move positions x to a deformed position x prime, so we have x prime of x. We talked about that already once when we talked about using B-splines as a means of computing these deformations or of representing these deformations. But never mind, you have an x prime of x, and the x prime positions don't correspond to the original x positions, and we have to worry about interpolation again. So whenever we're going to do any of these transformations, whether they be the so-called symmetry transformations, Euclid's symmetry in Euclid's sense, right, where scaling is, a scale triangle is similar to the corresponding unscaled triangle, where a rotated triangle is similar to the rotated triangle. Translated, okay, that's similarity in Euclid's sense of similar triangles. You studied that in what, 9th grade, 10th grade, 11th grade, somewhere along that way, right? Those similarity transforms are up above for translation, rotation, and scaling, but we also have deformation. All of them are going to require interpolation. And so we have to think about interpolation. Okay, there's a reference in Birchfield. Now let's talk about an interpolation operator. Any interpolation operator that we're going to think about. We'll use linear interpolation as an example. In one dimension, you have equally spaced points, and now I want to get a new value here. Okay, this is x. And I want to get an intensity. These are all intensity values, and we want to get an intensity value at this position here. And what we end up with is an intensity at x1 here, an intensity at x2 here, and we're interested in getting an intensity at some value of x here. We'll worry about two-dimensional interpolation in a minute, and three-dimensional interpolation, but right now one-dimensional, simple linear interpolation. Okay, so in linear interpolation, you take the two nearest points, this one here and this one here, those x1 and x2. You consider the distance you are from x1 as a fraction of x2 minus x1. We call that t, and then we get 1 minus t times I of x1 plus t times I of x2. Let's see, at 1, if I got that right, let's see, at t equals 1, this is 0, and you get I of x2, and t equals 0, you get I of x1. No, yeah, that's right. Okay, that's the formula. Okay, the point is that this multiplier is a function of x, x1, and x2. And you have the multiplier in front of I of x1, which is some coefficient. I just told you it's a function of x, x1, and x2. And you have a different multiplier that's also a function of x, x1, and x2 times I of x2. That's linear interpolation. Okay? the point is that, first of all, this is a linear operator. How do you check whether something's a linear operator? Rebecca, can you tell me? Is she here? Okay. Okay, go ahead, Madison.
It has to be homogeneous and additive.
Say again.
It has to be homogeneous and additive.
Yeah, homogeneous. I'll correct that. When you look up in the dictionary the word homogeneous, it says it's an incorrect form of homogeneous. Okay, so anyway, sorry for correcting your pronunciation, but okay, so homogeneous. What did you say now? Additive. Okay, so in other words, it needs to pass through addition and scalar multiplication, right? So if you take two images and interpolate it, and then add them, the interpolated values, or you, if you add them and then interpolate, you get the same result as if you interpolate and then add, or interpolate each and then add. Yes, that is a property of this. If I replace I of x1 with I plus j, I of x1 plus j of x1, and I of x2 by I plus j, it's the same, it's going to be the same as if I just did it on I plus j after you first add them, or you do it separately on I and j. Similarly, scalar multiplication, right? So you multiply I by 3 everywhere. That's scalar multiplication. And you can either interpolate 3i or interpolate I and then multiply by 3. And yeah, you get the same. Oh, it's a linear operator, right? Interpolation is linear for linear interpolation, but that's true for any function. If I, instead of taking the weighted sum of these things, I take, the square root of the sum of the square, I don't know, some fancy things that some fancy other, it's still going to be, I can apply each to a sum or a product, and I'm going to get the same, I'm going to be invariant. The next question is it shift invariant? Well, if you take an image and you take all those pixels and you shift them, and then you interpolate in the shifted image, and then you shift it back, is that the same as just doing interpolation in the unshifted? Yep, ooh, it's shift invariant. Ooh, if it's linear and shift invariant, then what can we conclude? What do we know about every linear shift invariant operator? This was in the third major point in the course. Linear shift invariants always have
the same eigenvectors. The same eigenvectors.
That's true. They have the same eigenvectors. That's true. But the big thing is they always have a convolution kernel. Any linear shift invariant operator has an associated convolution kernel. And therefore, in the frequency domain, it has a transfer function. And so it's useful to think about interpolation operators in terms of their kernels and their transfer functions. And so we're going to do that for linear operators. It says that right there. Every interpolation has a convolution and a corresponding, well, I use the word filter there, yes, or transfer function, same thing. Yes?
I'm a bit confused on how it's shift invariant, because couldn't you shift it so that all the points are already where you know intensity value, so you don't have to interpolate at all, and then that would be different than interpolating and then shifting?
No, when we're shifting the whole image, so it's resampled So it sampled the old pixels.
We have to shift like the whole number of pixel values, basically.
No, it's just that when we shift, we're shifting the pixels along with it. So in other words, the pixels are relative to the places in the image. If I have an image of my hand and I happen to have pixels that are at the finger places, and now I have a shifted hands, but the whole image is going to shift. And so I'm going to still have pixels here, 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 here. Okay? You're absolutely right. If we don't carry the pixels along, then it's not it won't be what you said it won't. But I'm talking about taking the image and moving it so that the sampling positions are at the same place relative to the pixel range as they were before.
Okay.
Okay? But extremely good point. Okay. So let's think of interpolations in terms of their convolutions. In terms of so now top needs to be here. Consider that kernel. It goes like it says from linearly from 1 pixel position at 0 up to 1 at the next pixel and back down to 0 linearly. If you think about that, then the multipliers at this position, don't say this. Let us now consider this guy as a kernel, meaning it has to be centered at the value at the output position. So we're talking about here. So I'm going to center it here, which means it's going to be like so. Nope. Yeah. And if you think about the values of the function, I'm sorry, this dash function here and here, they're exactly t and 1 minus t. What I'm saying is that a convolution kernel centered at the output position, which is this triangle function, gives you linear interpolation. Put another way, linear interpolation is convolution with a triangle, with a triangle kernel. Oh, cool. Now that we know it's linear interpolation is convolution with a triangle kernel, let's do Fourier transform of this triangle kernel and understand it in the frequency domain. Okay? By the way, notice that at the base situation, the value at, for example, here is 1 times the value here, plus 0 times the value here, plus 0 times the value here, which is sure enough interpolation. Right? So it is an interpolation. Okay, well, here comes an interesting property. We saw this when we talked about convolution, and we looked at an example online where we saw a movie of rect mech as a weighting function passing by rect. And we saw that if we had a rect here and we were applying a kernel which was a rect, that it had to do with the overlap, and it was linear with the overlap. What we learned was that triangle of x was simply rect involved with a rect at some appropriate width. If that's so, the Fourier transform of triangle is the product of the Fourier transform of rect and the Fourier transform of rect. Right? Because it's convolution between the two. But the Fourier transform of rect is sync. Sine something, sine ax over ax for some a. Oh. Nu. It's a sine squared over nu squared function. And there's a picture of that sine squared over nu squared function. Sorry about the t, I copied that off. It's where it says t, you should see frequency. The point is that it's an envelope that looks like 1 over nu squared, both above and below the axis. And in it, there is sine squared. Sine squared is always positive. So this sine squared, sin squared. So the envelope is 1 over nu squared, and the function is always positive. But where sine is 0, it's 0. Except at 0, where sine x over x looks like 1 in the limit. That's what linear interpolation is doing in the frequency domain. Among the things it's doing is canceling all the frequencies that are multiples of pi, integer multiples of pi, right? Because that sine function is 0 there. And it's also damping the amplitudes as a function of frequency. The 1 over, and it's damping it by a 1 over nu squared sort of function. It's doing blurring. It's making the higher frequencies, the coefficients there, lower by a factor proportional to 1 over nu squared. So now we understand that linear interpolation is something you can do, but when you do it, you are having these effects. You're throwing away information near the multiples of the zeros of the sine function, and you're blurring, you're lowering the amplitudes of information at higher frequencies, like 1 over nu squared. The point is that we can do this same kind of, since every interpolation operator is going to be linear and shift invariant, we can play the same game whichever interpolation operator we want to have. This was just an example for linear interpolation. So we can do, let's say, quadratic interpolation. So instead of just using the two nearest positions to where we want a result, we use the three nearest positions. Okay, so we have the value at some x, and we look at the three nearest pixel positions, and we make a formula that's a quadratic that has the property that it passes through all those positions. And that has a kernel, and we can analyze the kernel, and we'll see that when we do that, we'll get, again, some function that falls with frequency in the frequency domain. When we look at the filter, we look at the convolution kernel, but in the frequency domain, we understand it to be a transfer function of the kernel. We'll see that it also falls. It falls less fast than 1 over nu squared. Right? In other words, it still damps, but it doesn't damp as, it passes better for somewhat higher frequencies. That is to say, for somewhat smaller levels of detail. Okay, we're going to do cubics. We can do cubic interpolation. We saw that there exists a spline interpolation that is interpolative. It's seldom used, but okay, we could. But anyway, the upshot, then you're going to use 4 points, the 4 nearest points. And you're going to interpolate a polynomial through the 4 nearest points. Oh, we saw that with splines. Yeah, it always is based on 4 nearest points for splines, yeah? And again, we're going to have that the damping is even less, but it's still damping. It's going to pass even smaller levels of detail to some criterion level. It's going to nevertheless damp as a function of frequency. Okay, so the general idea is that we can do these polynomial-based interpolations, linear, quadratic, cubic, essentially by adding more and more nearby points for the interpolating function. And we get more work, harder to do, less damping as we increase the order of the polynomial. Okay, 2 minutes to go. I want to say something about, so far we've been talking about one-dimensional interpolation, but what about two-dimensional interpolation? So now we have pixels, and we have a place we want to interpolate, and we look at the 4 closest pixels, 2 in y and 2 in x. In 3D, there's going to be 8. 2 closest in x, 2 closest in y. In other words, we look at in which square of pixels this x lives. And in 3D, there's a cube, and we look at which little cube x lives in. And so we want to interpolate at x. And the way we're going to do that is we're going to take these 2 pixels and we're going to interpolate it at this x position, and these 2, and also interpolate it at this x position via linear interpolation. So we're going to do this separately. First, we're going to do rows, and we get the values here and here, and then we're going to do a linear interpolation between this and this, and we're going to get a value here. So first linear interpolation on the rows and then linear interpolation in the column direction. That's called bilinear interpolation. It's very commonly used. And would you believe that you can work out that if you do it in the opposite order, you get the same result? So we could instead interpolate here in y and here in y, and then interpolate between those two in x, and we'll get exactly the same result. Yeah. This is what splines do? No. It's different from splines. They're separable also, but they're not bilinear. In fact, they're bicubic. The B-splines that we talked about. Anyway, so look, the point then is that since this is separable, we can talk about a convolution in the x direction and a convolution in the y direction, and each one of them has this damping in x frequency and y frequency respectively that looks like this thing in the upper right. Right? It's just a cascade of an x interpolation and a y interpolation. And so you got an x convolution in this, multiplication by this thing in this x direction, followed by an x effect in the y, multiplied by in the y direction. Okay, so end of this lecture. The major point I want you to take away is that linear interpolation, interpolation in general is linear and shift invariant, and therefore we can analyze it in the frequency domain, and it's very worthwhile to do that to understand what interpolators do. Next time we'll talk about, well, if these damp too much, how do you get it so you don't damp? And we'll talk about that.